Okay, so yeah, welcome everyone. I think we can slowly start with the talk. It's already 3 p.m. It's a pleasure to be here to talk about table inheritance in PostgreSQL. And yeah, just a short start while everyone's settling down, while people are still coming. Who is this guy that's up front here speaking? My name is Victor. I'm from Brazil. And exactly 3 years ago, so 16th of September 2019, I started at InnoGames as a software developer. And in these 3 years, I have been working on the Forge of Empires project as a backend software developer. And one thing that is in common from my InnoGames work and also my previous experiences that I have worked with some different entity relationship database, and in all 3 cases, I have worked with PostgreSQL, which will be the main subject today. Also, I have spoken about InnoGames. You probably have seen it on this couple of days because we are one of the sponsors of this event, so we probably have met Max and Stefania at the booth that you have here. And we develop free-to-play games, both on browser and mobile, so I think I'm not covering all of them, but we have here listed as browser games Forge of Empires, Elven, and Grapolis, while we have the new mobile games Rise of Cultures, Sunrise Village, and Lost Survivors. And nowadays we are more than 400 employees. Our company is based here in Hamburg, but with the recent world changes, we are working on a hybrid model. And yeah, last time I have checked, we had 7 open vacancies. So if you or some friend wants to work on a gaming company, I can totally recommend. Not only because of me, but as you can see, it's a certified great place to work. So what I'm going to present today is about table inheritance. So I'll cover what is the definition of table inheritance, how to use them, how do queries look like, and I'll bring in the good news and the bad news. So on the good news side, the performance, so what can it bring to the table and how is it good for you, and also its limitations, because nothing is perfect. And then I will show a couple of features in Forge of Empires where we have applied the table inheritance and how we make it sustainable to easily add new inherited tables, new parents and children, and how to scale it easily. And we'll add up my final considerations. So what is table inheritance? Before I bring in the final definition of that, the main reason why I researched and worked with table inheritance was checking different designs in relation to database. I have highlighted a couple of them that I personally dislike, and also on the team I don't think it's optimal, but in some cases you might be working with them, you might even see them, and you might even have them and do not notice. And the first case is when you have single tables, because they start to grow horizontally. So you start to patch some features, you see something that kind of resembles that, hey, I have a new vehicle, I can just extend a new field here and there. It can be nullable because I do not want to use in every single case. And then we have lots of cases. The table just grows horizontally. We have a mix of nullable columns. We have a type string column that will just rule everything. And that's not really optimal, because even though we can have a very solid logic that will determine, like, okay, if I want to add a car, those 3 fields will be filled. If I want to have a truck, then the other 2 columns are going to be used. At the end, we might have inconsistent data. If I go directly to the database by any reason and add a mismatch of nullable columns, that will still be valid. And when it's loaded by our project logic, that's probably going to create some undesired behavior. On the other side, you could have multiple unrelated tables. So speaking of this example of a car and a truck, I do not have any link between them. So they'll have these duplicated fields. In this case, I have highlighted the manufacturer, the license plate, and the mileage. And what's bad about that is if some rule changes, I have to go to every single place and fix them. So let's say I now have a manufacturer manufacturer table, and want to use the column with a foreign key, I have to go to every single place and fix that. Or if I have like some char constraint in the license plate and we have a new rule in place, they do not use 8 characters anymore, they use 7, I also have to go to every place manually and fix that. So we usually go to the one-to-one relationship, and on a diagram basis it looks like the same as to one-to-many or many-to-many, where we have a center table with all the common data and dedicated fields going to separate tables. So in the example I was showing before, I hope I'm not covering and spots here. Then we have the manufacturer, license plate, and mileage that will be common to car and truck in one table. And each of those two have their own tables, and as highlighted in blue here, they will have their own serial primary keys, as well as a foreign key to have a reference to the vehicle. And we also can have a fourth design, that's the table inheritance. So if you look at the diagram, you pretty much see that it remembers the object-oriented programming. We have a parent, that's the vehicle here, and both car and truck inherit all the definitions from the parent. And also, if you compare to the one-to-one relationship, we don't have foreign keys, and we also don't have a serial primary key for car and truck. And that's pretty much what table inheritance is. It's a concept that has been ported from the object-oriented databases, and when it comes to entity relationship database, for now it's only available on PostgreSQL. We do have some other mechanisms in some other types of database. For example, in Oracle, we have the object views, but then we are creating objects out of them, and we are inheriting both behavior and structure. So when it comes to relationship data and structure, Postgres for now is the only database system that provides it. And if you take a look at that, it pretty much resembles the OOP, and what we can highlight from that is that every children will inherit the columns that are declared in the parent table. If you want, and the parent table has indexes, you can also inherit. It's optional, not mandatory. And some of the constraints are inherited. Some cannot be inherited. I will highlight them in the drawback session, but for now, at least the check and not null constraints will be cascaded. And also a feature from Postgres, there are partitions from the parent table, which optimizes memory disk usage. But as I said, it's only about structure. No behaviors are inherited. I don't know if the picture is clear enough because of the light here, but we have a Renault car from 2012, and on its first concept, this car didn't have any doors. So you can see it has a license plate, it could run across the streets, but if you have a system and the car needed to implement a method open door, this car will probably create some troubles to your application. But on database side, it's pretty much acceptable, until we come to some point where we add some doors and constraints. But if you're talking about the example shown above, everything would just be perfect on table inheritance. So going to the practical side, I hope I'm also not covering and that it's pretty much legible and not blurry. But how do we create tables that inherit each other? So to create the parent table is pretty much business as usual. You just create a table, declare its columns. If you have some other constraints you want to add, you do it, you run the query, and you have it. But when it comes to the child table, there are two things that you might want to use. So the first one, as I said, is the like with the parent table including indexes. It's an optional feature, and in that case, if you have indexes regarding, I don't know, some check constraints, some filtering, those will be inherited by the child table. And the second one, most important, is that last column, the inherits with the parent table in parentheses. That is going to create the inheritance in Postgres, and as you can see after running the query, we even have the declaration that ID, manufacturer, license plate, and mileage all have been inherited, and they are part of the car table. It sounds pretty easy to create, and now we have a couple of tables inheriting each other, and you might be wondering, how do we run queries within these child tables? And it's even simpler than the one-to-one relationship, because if I want to add data into the car table, I can add everything directly. So in the query example that we have, first we send all the columns, including the parent ones, in one single query. You add it, and if you run the query, data will be added to the database. So I have run these three queries here, so one for car, one for truck, that's a different child, and one for vehicle. So I'm inserting data directly into the parent table. Then, yeah, I select everything from the car, and as you see, I get all the columns filled correctly. I get the ID number 1, it's a serial, so if you check the truck next, you see that the ID has incremented, so now the truck is number 2. So it's also a good sign that, okay, it recognizes that it's part of one single structure, those IDs are not shared between parents and children, and they have been incremented. Now, if you take a look at the last query, the select star from vehicle, I will get the 3 rows that I have inserted, so one for the car, one for the truck, one for the vehicle. But if you pay attention, you only get the columns that belong to the parent table. So I missed the information about max speed from the car, I missed the information about the height from the truck. And one thing that we can do is to add the natural full join. So when I do that, it means that I will bring every piece of information that belongs to that specific child. So you can see that both the truck and the vehicle, they do not lose any information. They have those columns shown as if there are no fields because they have not been filled, and I get the columns from the car. And yeah, as a second example, I have done the query with full join to car and truck. So what the query inputs me, it's pretty much like that single table, but that's only the result of the query. I get everything here at once. And if by any chance I also work with inserts to the parent table, I also have a way to recover information that has been added directly on that table. So as you can see here, I can use the keyword only before the table name. And if I run select star from only vehicle, that will get me that motorcycle that I have added. So it's not a car, not a truck, it's just a vehicle. So it looks pretty simple from the query side to work with table inheritance. And maybe you want to try it out in one of our projects. Maybe you're thinking, okay, that looks nice, but I'm pretty much used to the one-to-one relationship. What does table inheritance bring to me besides a design that I pretty much know? And the answer to that is performance. So I have created a testing scenario here where in the same environment I added a similar set of tables with table inheritance and the one-to-one relationship. In both cases, I have added 500,000 car rows, 500,000 truck rows. So in the end, you have 1 million vehicles. And in the one-to-one relationship, I also had to add 1 million rows to the vehicle table due to the foreign key reference. And when checking the memory consumption from this scenario, what I get is that the 3 tables from the one-to-one relationship altogether, they are near 150 megabytes, with the table inheritance only 90. So that was almost 40% less disk space. So please take that with a grain of salt, because that belongs to this scenario, this amount of rows, this number of children. So maybe you have a table that has less data, and that difference could be not 40%, could be a bit smaller. Or if you have 10 children, in that case, maybe the difference will not be as high as this one. So this is just to highlight that the difference can be considerable enough, but each case is a case. So maybe your application will have 30%, 20%. Do not benchmark this specific number. I also wanted to test the performance of the queries. So what I did was to run the explain analyze query. That's a feature from PostgreSQL that if you run that before a query, it will execute that one and provide the results. So it will provide the filterings that it has provided, the costs, indexes, cache misses and hits, and at the end we will show the planning and execution time from the queries. So what I did, I tested scenarios with the common queries. So insert, delete, update on those 2 scenarios, run that scenario some dozens of times, and brought on the average of them to compare how much performance they can be. So for example, when trying to insert that in the one-to-one relationship, I have to run 2 queries because of the foreign key relationship. And that altogether took me 0.25 milliseconds, which is pretty fast. But when doing that on the table inheritance, I only needed 1 query, so I saved 0.1 milliseconds from the first query. It's a slight improvement, but yeah, every millisecond counts in that case. But there are cases where it was a bit more prominent. So if I check the update, and let's say in that case that I want to update 1 column that belongs to the parent and 1 column that belongs to the child. When I do that in the one-to-one relationship, I have to run 2 queries because those fields do not belong to the same table. And that overall brought me to 0.4 milliseconds. While doing that on the table inheritance, I can run 1 single query, both columns will be updated at once, and was even a bit faster with 0.17 milliseconds on average. Still, that's a short difference, but then here the results start to get more interesting. If I want to run the delete, in that case here I have run it in two different scenarios, because we could have deleted it first from the car, then from the vehicle, or I could have the delete cascade constraint. So as soon as it deletes from the vehicle, it will check like, hey, you have a car that has a communication with this vehicle, delete this car altogether. And with the constraint it was slightly faster, so I took the best result. And checking the constraints and triggers, one deletion query took me 70 milliseconds, which is a bit higher than the insert and update queries, but 70 milliseconds can be a reasonable time depending on your application. But when I do that on the table inheritance, I can just delete the car, and all the data that belonged either to that car or the vehicle columns is gone with one single query. And that took me 0.2 milliseconds. There is no typo here, it was really 70 milliseconds against 0.2, which is a huge difference. So if you consider an application where data is updating pretty frequently and you're going to do lots of deletion queries, that's something that caught our attention that we want to make use of. Then we also have the select queries, and yeah, they will be the most common because that's what you do, you retrieve data every time. And if you want to get all the data all together on the one-to-one relationship, it took approximately 1.4 seconds. If I do that with the natural full join on the table inheritance, it's a bit more than 1.5 milliseconds, so that's slower. Okay, why I'm listing that as a positive fact? That's because if I want to get dedicated data, it's way faster, and I can even twist the logic a little bit. So if I want to get everything that the car has with all the columns that belong to the car and also from the vehicle, the one-to-one relationship takes me roughly 570 milliseconds, half a second to do that operation. When I do that with the table inheritance, only 75 milliseconds, which was 7 times faster when I do that. And if I combine that, I can do the select everything from the car plus everything from the truck, that will be even faster than the query that I ran before with the natural full joins. So even to get all the data split into all the child tables, it's even faster to get data from one single table on the one-to-one relationship. But usually we're not selecting all the data altogether. We usually apply some filtering due to some condition, and in our nature, as we are referring to a game, we're usually selecting data from one specific player. So I mimic a scenario here where I just want to get 100 rows from that condition. So from the car to get 100 rows out of the 500,000, it took me half of the second of the regular select query, 280 milliseconds on average. And that result for the table inheritance was even faster, 0.17 milliseconds. So if we're dealing with a feature that we're frequently selecting queries with filterings and want to do deletions, updates, inserts, it's pretty much faster. It gives me a huge performance boost. So that's something that caught our attention, like, hey, why not try it? But yeah, it's also important to mention that it's not a perfect feature. Otherwise, it would just be used everywhere. It would be the new standard, everything that everyone's talking about. And there is one specific drawback that goes into one direction that I'm going to show you why it fails. And that's about constraints. When you talk about the check and not null constraints, they are inherited by the children. So if I say that the license plate cannot be nullable, and I try to add that to the children without using the license plate, it's going to fail. That constraint is inherited. But unique primary key and foreign keys, they are not inherited, they are not shared. They belong separately to both tables. In two cases, we can overcome the situation. But yeah, I'll show you how does that work and why that it can be bad. So with the foreign key, I took the example that I could have a manufacturer table. So here, instead of adding the name directly, I would have a separate table with some information. And now I want to reference the manufacturer ID on my parent table. So if I try to add that to the with ID 2, while adding it directly to the vehicle, it will say that I cannot do that. I violate the constraint because the ID number 2 does not exist. But if I try to do that directly into the car, as you can see, the query ran. So it was a bit strange, like, why I don't have this ID 2, I have a foreign key. And even if I run a select query directly onto the vehicle, I can see that, okay, I have a manufacturer ID number 2, which is pretty much inconsistent. If I run that in the application, it will probably break my project. Say, hey, I'm trying to load some data that does not exist. There is a simple solution to that, even though it's not elegant, is that we can apply the foreign key constraint also to the child. There won't be any downsides to that. They will pretty much behave the same because they refer to the same single point of truth, but the foreign key constraint is something that we can overcome. When it comes to the primary key, you probably have seen before that I added a car, a truck, and a vehicle, and the IDs have incremented. So why are not they being inherited? Here I have 1, 2, 3. The issues happens here when we try to add this ID explicitly. So if I go here and try to add a new vehicle with ID 3, it's going to show me, hey, you cannot do that. It violates the constraint vehicle primary key. The ID 3 is already there. And if I try to do that with the car, with the ID 1, it will say the same. You cannot do that because the ID exists. But it says here that I'm violating the constraint car primary key. It's not a vehicle primary key anymore. And if I then try to insert IDs that belongs to the other child's tables or to the parent tables explicitly, they will allow me to do that. And in the end, if I try to get everything I have from the vehicle, I have 3 times the ID number 2. And we're talking about a field that is supposed to be unique, that's probably going to rule out our application, and that you're going to do a reference to other tables. So yeah, that's not something we want. We cannot allow these IDs to be duplicated. So there is one solution to that, and that we never should insert these primary keys explicitly. Of course, there will be some situations where this doesn't happen by any reasons, by the nature of your project. And yeah, in that case, that cannot be avoided. Then it's a case where table inheritance is not recommended at all. But if you just work with artificial primary keys where the number doesn't matter and they can just increment, then okay, then do that and never add the ID explicitly. But there is also a problem without solution, that is the unique constraint. I have just shown here with the primary key that this constraint was not shared, and it's the same with the unique. Let's say that the license plate should have a unique constraint because we are not supposed to have 2 cars with the same license plate. And then I try to add a second vehicle with that license plate, and the database tells me, hey, you cannot do that because we already have a vehicle with that license plate. But I can do that via car. So if I add now a car that has that unique field, Postgres allow me to do that. And just showing it here, I have 2 rows with the same license plate. That's supposed to be unique. And that also happens the other way around. If I add the constraint to the car and then try to add it as a vehicle, it allows me. So the unique constraint is not applied at all. And unfortunately, that's a problem without solution. So again, if you need to have uniqueness on a field that belongs to the parent table, then table inheritance definitely is not the case where you want to apply that. So having spoken a bit about the positives, the drawbacks, we also came to, hey, we want to apply that on our project, so the game Forge of Empires. And yeah, we have applied that to some of the features. I'm going to show a couple of them and how does it work for us. And the first feature that received the table inheritance was the notice indicators feature. So as soon as you load the game, you get some information that's shown on the game start, and we have those icons that show you, hey, you have something new. So for example, in the first one, you have the quest, that, hey, you have completed the quest, check it out and claim your reward. Or you have unlocked a new building that you can place in our city, and then you have this exclamation mark that, hey, this is new, maybe you want to check it out right now. Or if you got a new item, that you just show, hey, this item is new. So you have got a certain amount of that item. And the problem is that it was using one single table and was expanding horizontally. So we used one feature that had that, and that, hey, we also want to add indicators to a second feature. So let's add that, and we can have nullable columns here and there. And oh, we want to have a third case, and now we will need even an amount that can be nullable or use the default. So it was just expanding, and that would go non-stop, which is not really what we want to achieve. And then checking that, and the definition that we have seen, just check that, hey, maybe this is a good candidate for table inheritance, because from the common fields, you're not going to be affected by the drawbacks. This is a feature that's required on the game start, so it's less loading time for the player. So, hey, let's do it. And while I was talking about the database, that's how the table looked like before we made some changes. We had lots of nullable fields here, including primary keys, so could have a broken reference when we misuse that. We were using default fields that pretty much were irrelevant to some of the cases. So for the quest, it's just like a check mark. I don't need an amount, but I was saving that with amount 1. And we had that type string column that was ruling everything. So I would say, hey, I got a new item or I got a new building, and you're having to rely on a string column to run that logic. So after some refactoring, what you came up was with that design on the table inheritance. We just have one main table with the common columns. In that case, pretty much simple, only the player ID and the serial, and then you could split into the different features and the columns that they needed. So yes, for the building, it's a string, and that's because we load from a config, so don't use integers here. So please do not take the strict type into account on that one. It's a different logic. Also for the items, that, hey, which is the ID of the item from a different table, and how many did you get that are new that you want to show. And also for the quest, which is the ID of the quest you have just completed. And about unique constraints, we could even combine, because the unique constraint referenced the child field. So for each of them, we could make sure that, hey, the player doesn't have a building twice here in that table, which was pretty useful and helped us to have better, consistent data. Also, design-wise, it looks cleaner to us that we have this information extracted and not this combination of null columns where you have to juggle through the columns and fields and see what matches and what not, and if data is consistent or not. And also, most importantly, feature performance, especially talking about something that's loaded on game start, that players will be interacting the entire time. That's pretty much what we want. Better performance. And also I brought some code snippets on how do we make it work on our project. So what we have here is a gateway that would be the class that we communicate with the database, and we created an abstract class for that to make sure that we could also use the abstract factory pattern. Just also one adaptation here, because we often see the definition with interface, and here we can use the gateway with some other features, so that's also why you have an abstract class, not an interface here. But overall, what we have is that we have a common set of methods that should be implemented. So if you want to select something, here's the get, so for which player you want to get. If you want to add something to which player, and the payload comes in an array, so we can freely extract the fields we would need in that case. And if you want to clean them all for one player, which player ID we want to have. And we also made use of the service locator pattern here. In that case, we use Symfony for PHP, then making use of the service locator that they provide. And what you do is that we then extend that gateway and implement the queries that we want. We can also use plain SQL queries here, or you can use object queries. Both work fine, but yeah, here's just to show that, hey, if I want to get, I'm selecting from that table, and that for every child. And then if we look inside the code again, we would have a model that calls that service locator, and let's say I want to delete everything from a specific type, so hey, clear them out for the items. I will get on runtime which is the gateway I want to access to delete that, and then clear out everything for that player. So yeah, then we could apply those two design patterns to make it work nicely within our project. And then if you want to add new children, or if you want to have other table inheritance, if you want to add a parent, because you can have multiple inheritance, you could still extend and have grandchild tables that works until 10 levels. So if you want to add something new to that, first we can just create or adjust the parent table. Maybe you want to include some other data, maybe you need to do some adaptations. Then yes, the second spot, we can create a child table with the definitions that it needs, if it's on columns. And also if needed, if you're refactoring something, if you're just migrating the database, we add a query to shift the data into the new format. And going to the code side, we can create a dedicated gateway, and we will implement both the service locator with the dedicated queries and the service map tag, and implement the methods from the factory to make sure that we have all of the important and mandatory queries there. And also, if you have some queries where we get data overall, as shown with the vehicle, that we could use, hey, select everything from the car, select everything from the truck. If that's also needed, we then also add the newly created child table to the mix. And it makes pretty extendable. We can also have the node syndicator easily for other features now with different looks. And there's one thing that we have to keep an eye out, that is on the migration step, because that's pretty much manual and unique for every case. We cannot have a one-size-fits-all approach to that one. And one thing that's important is that if I have reference to the table that I'm migrating, I might lose some IDs and I need to adapt them. Just because it's easier to migrate data from each of the children directly at one time. So let's say, for example, in that initial jar, I have the blue ball with ID 1, then the yellow ball with ID 2, the red one is ID 3, and so on. If I migrate the red ones first, they would come up with the first ID, so 1, 2, 3, 4, and then the reference to the blue and the yellow are broken. So if they are foreign keys to other tables, please, we have to pay attention to that to do not lose data. Then also another feature that I want to highlight is the boost system that we have in our project, because boost is a pretty much relevant feature throughout the game. Forge of Empires is a city builder, so as you can see on the right side, I have a boost on supply production, so pretty much the base mechanic of the game is going to make use of that boost, and that has to be loaded anytime that I want to collect something from one of the buildings. If I want to check my output, that needs to be there. Also, battles are pretty much an important feature to have queues and progress for them, get rewards, and as shown here on the left side, during a battle, for every single step, for every single attack that I'm going to make, or if I'm taking some hits, boosts need to be here and there. So it's a mechanic that's highly used, and performance impacts. Just imagine that the boosts are not optimal, and then you have a slow battle that brings a very bad user experience. Or if I want to collect something from the city, and players have to wait because they're calculating boosts, information is wrong, then that's not what we want. And that was how the boost used to look like before. So we had not nullable columns that were used in specific situations, so we even had on code logic to add some data to them. Also, some plain strings that used only in specific situations, and nullable foreign keys. And taking the same approach that how it looked like afterwards. So the boost table contained a bit more information because there was more data shared on between those two. And for the buildings, we could then have like the foreign key there. In that case, it didn't even need a uniqueness by logic approaches. And for the feature boost, so where was the main source of that feature and when did it expire, because some of the boosts would be there forever. That brings me to the final considerations. So I have brought some comparison between the one-to-one relationship, and they are still two very good solutions. So it's easy to add and remove columns. Parent columns will not be duplicated. It's very easy to scale and add dedicated data. But if I want to get specific data, table inheritance gets my point here, because I don't need to join. I just go to the car table in that example, that hey, brings me everything, and everything is there. Also, if I want to get all data when it comes to one-to-one relationships, I need to run some joins here. And on the table inheritance, I can either run the natural full join, or I can run 2 queries or more for that. And on maintenance, both of them have their downsides. So for the one-to-one relationship, I need primary and foreign keys here and there. I need to know them and retrieve them every time. And the table inheritance, I really need to pay attention to constraints. So yeah, that is also pretty much sums up the pros and cons from the table inheritance. Yeah, on the pros, pretty much the design, the query syntax, that's very easy. There's disk space, performance, and yeah, it's easy to implement and to scale. And yeah, also on our code, it gives us a very clean result with abstract factory and service locator. But yeah, for the cons, we can have inconsistent database states, mostly because of the constraint drawbacks. And also because that's a feature that when it comes up to entity relationship database, it's exclusive to PostgreSQL. So overall, my conclusion is that the table inheritance is a very useful feature, mostly because of high performance and also a very good design. And for me particularly, when designing a new feature and you come up with what we want to add and have there, it already gave me a new mindset. I already started to look, even on database level, how things can interact and if there are things that are common and need to be inherited. And when it comes to code level, it also gave me a better approach and overview overall. But it's also important to highlight that I'm not discrediting the one-to-one relationship, and I do not want the table inheritance to take it over. The important thing here is that you pay attention and see if you can profit from the benefits and that the drawbacks will not be an issue for you. And yeah, you have to choose it wisely when it makes sense or not to use the table inheritance. Otherwise, you start to facing some problems, and at some point you say, oh, I hate this feature. Why did I listen to that guy talking about table inheritance? And maybe that's just because it was not the best case for it. So that pretty much concludes my presentation here. I think we still have some minutes for questions and comments, but overall, I would like to thank you all